According to data from Statista.com, the average price of a new home sold in 2020 in the USA was $391,000. According to Climate Change Realty, the price of finding your real estate agent and creating thousands of dollars in donations to support climate action is and always will be $0. Welcome to the podcast. Ryan, great to meet you, man. Thanks so much for taking some time to come on the show. Excited to have a chat.
Thanks, Ethan. Glad to be here. Excited to dive in deep into Bloom.
We're going deep into Bloom, man. But before we do, we always like to get a little bit of background on who you are and how you got to be doing what you're doing at the current moment.
Yeah, so I'm Ryan Hunt. I'm the co-founder and CTO of our company Algae and our brand Bloom Sustainable Materials. And my background is in physics. I'm a scientist. I've been studying sustainable materials and bioengineering for almost 15 years now. I've got degrees in both physics and bioengineering and from the University of Georgia. And during grad school, my very first project was turning pine trees into a green crude oil. So that really is what got me excited about this whole idea of sustainable products and technologies. And that evolved quite rapidly out of trees and looking at other waste products that could be interesting to explore. And this is when I came across a big paper published by the Department of Energy called the Aquatic Species Program. And this was like almost 25 years worth of research done by the federal government and national labs on using algae as a feedstock for making biofuels. So that started in the 70s and then finally ended in the late 90s, mid 90s. And all that research that was done is publicly available. And so when I was in grad school, I downloaded that report and started reading all about algae and how fast it grows and how it absorbs CO2 and converts water pollution like nitrogen and phosphorus into biomass and how we can use that biomass to replace petroleum. So that really caught my attention. And I started working at the university on this what was actually called a pyrolysis project. We're using heat and pressure to convert the trees into oil. I convinced my professor to switch from trees to algae. The problem was, it's easy to get trees, right? They're everywhere. You just go call up a landowner and ask for some chips, right? It's super easy to get pine trees. Getting lots of algae to experiment with, not so easy. So the first couple years of our program was spent isolating and identifying specific strains of algae that were growing in the natural flora and trying to get them to grow as fast as possible. And really what we found was that when you blend the algae with nutrients from, let's say, wastewater or industrial wastewater, municipal wastewater, agricultural wastewater, the excess amounts of nutrients, the nitrogen, the ammonia, the phosphorus, these are all, fertilizers for algae. And so we found that we could clean water as part of a service through a wastewater treatment factory or process, and then use that biomass as a feedstock for, XYZ process. And so our group had a lot of cool toys. We not only were growing the algae and scaling that up, and then harvesting it, we were drying it, we were extracting oils from it, we were feeding it to chickens. We were also looking at it for soil amendment. We were making biochar out of it. We were gasifying it and turning it into hydrogen and syngas. We were pyrolyzing it and turning it into crude oil. But finally, actually, the last thing we kind of looked at was thermoplastic co-processing or extrusion. And there, ironically, was this. We had a old extruder from a previous grad project from years before, and it was like in pieces in one of our storage facilities on campus. And I identified. I was like, I think I know what that thing is. And sure enough, we pulled this thing out, knocked off the dust, cleaned out the rat poop, and got it rolling again. And we started feeding algae and different types of polymers into that machine, melting down the polymers, basically denaturing the algae, which means that you're essentially kind of like unfolding and breaking open the algae cells, but you're not totally like burning it or destroying it. It's kind of an intermediary space. And when you blend these two things together, we were creating these composites that had interesting natural thermoplastic properties. And that's when the light bulb went off that, hey, maybe we can use this algae not as something we're going to burn in a fuel tank and just re-emit that CO2 right back into the atmosphere, but rather for applications where we want to displace petroleum and get a high value out of it. Can we use this algae to displace plastics? And this is like in 2008, 2009. So, bioplastics were still relatively new. I mean, PLA had been around for a decade or two, and the pricing had come down a bit, so it was commercial. But there still was. I mean, I think it was in the early days in terms of sustainability in the consumer market. So we struggled a lot. But that's really the background, was one of science, inspiration around algae, and using Earth's most abundant and most efficient photosynthetic organism we have access to, which are these microscopic, single-celled, or in some cases multicellular plants. The difference between an algae and a plant is that plants have roots, seeds, and stems. Algae does not. Algae it's more like almost like a bacteria, really. In fact, there are even bacteria that are photosynthetic called cyanobacteria or blue-green algae. So that also falls within this kind of broader classification. When people say the word algae, it actually represents over 30,000 different species of these different organisms all over the planet. So just a huge abundance of opportunity there. And while most of the funding was focused on biofuels in the early days, with our company that we launched in 2010, we made a 180-degree pivot away from fuels, and really were focused on how do we get as much value and how do we scale this up quickly, because to scale up fuels, it's like really hard. It's super expensive. It's super cutthroat. You're up against, the biggest, mafias of the world,
Right.
So,
Literally.
not an easy business to break into out of your garage. Right. And we were basically a garage startup.
Yeah.
So making products was, I think, a little bit easier. And so, and the equipment that we need, while it was millions of dollars, it was not billions of dollars. So
Right.
there's a few extra zeros when you start talking about building a petroleum refinery,
Totally. Can you grow it? Does it grow in the ocean?
Oh, yeah. I mean,
It
70% of the
does.
planet's water.
Okay.
So phytoplankton is typically what the word you'd hear associated with marine algae. But the biggest algae industry right now is kelp.
Phytoplankton and algae are the same thing?
Yeah.
Oh, I did not know that. We just did a whole like upwelling, downwelling episode.
Yeah. So phytoplankton basically means so phytos plant. It really references the photosynthetic apparatus, right? It's photosynthetic. Plankton is tiny, is small and floating, basically. So phytoplankton are basically these marine species of algae living in the ocean. There's a lot of them. We don't even know. I mean, like I said, 30,000 is what we currently have logged. That's not it, right? There's more we just haven't discovered yet or haven't logged yet. So, and that's that whole, I mean, as we're getting more genetic information, that whole taxonomy is being updated almost. I mean, what I learned in grad school 10, 12 years ago is like not even relevant anymore. It's all been probably changed a lot. So, but yeah, and then you also have what's called seaweed, right? Seaweed is a macro algae like kelp, and these are multicellular algae. They don't have seeds or stems or roots, but they're essentially these large multicellular versions of algae, and that is probably the largest commercial algae industry in the world. I mean, kelp's used for a variety of products. Cosmetics was one of the biggest ones, but also in food and feeds for animals.
Kelp
So
is different than seaweed, or is it the same thing?
kelp is a type of seaweed. It's a
Okay.
particular species or class of seaweeds. There's freshwater, there's saltwater, there's brackish water, which is kind of in between. Then there's also halotolerant or hypersaline species. So there's species of algae that like super high salt concentrations, maybe twice that of the ocean. An example of that is Dunaliella, which is a bright, brilliant orange, reddish microalgae that produces the highest concentration of beta carotene on the planet, by weight. So that's being
Beta
grown
carotene,
commercially.
is that the thing that turns your skin orange or something?
If you ate a lot of it, yeah, carrots, big carrots. If you ate
Right.
a bunch of carrots or a bunch of Dunaliella salina, you're gonna eventually turn orange.
Right. Is there any history of people like humans using algae in the past for some large, or not even large, just in small scale industrial use, or patting their house or something, or eating it?
Yeah, for sure. Well, seaweeds. I mean, kelp has been used, they think, for a long time as an aquatic plant that's used in more of the in Asia in terms of food. There are several edible strains of seaweed that have some historical reference. Microalgae is a little bit different. There isn't that much shown in large scale algae culture, microalgae culture. However, there is archaeological evidence that the Mayans and the Aztecs were cultivating microalgae, uh, back hundreds and hundreds of years ago, maybe over 500 years ago, and they're doing so in a way that they were using it to as a feed supplement. I mean, they had at the time one of the largest populations in any one location on the planet, and they had to sustain this population while also experiencing climate change of that time and deforestation and all the same issues that we kind of have today, but without any of the technology or engineering to solve those issues. They didn't have like wastewater treatment plants. So the thought is that as they've done excavations, they've been finding canals that have thick layers of algae residue in the canals. So either it was on purpose or it wasn't, but there was reports from the Spanish that talked about this cheese that they would, when they first came to the area in the Yucatan, the Mayans would give the conquistadors that let them try this like green cheese that they had, or is how as it was described by the Spaniards.
Sounds
and
lovely.
and that was like a fermented algae cake that the Spanish didn't. They thought it was really gross, basically.
Right.
But
So
they think it's basically an algae food, which might explain how they're able to sustain this massive population was because algae is a superfood. It's full of nutrients, full of protein and micronutrients and minerals. And so if you can grow this stuff and eat it just like we do today with our spirulina smoothies and super green food products, if you go look at the ingredients, spirulina, chlorella, these are species of microalgae that are rich in nutrients that are used in these modern day superfoods. So this could be something that happened in the past.
yeah, well, it's obviously it seems like an unutilized resource or opportunity or whatever you want to call it, or an amazing specimen of life on Earth. What exactly are you doing at Algix, and what are you doing with your brand Bloom, and how does like your business model actually work?
So we focused on using the algae as a material versus burning it. And so by doing that, we were able to create more value per pound of algae produced. Because if you're trying to go down a biofuel or a lipid or oil route, the algae only has so much of that in its biomass. And so we looked at, well, what happens if we could use the whole algae? What if we could take everything but the oil, all that remaining material, and use it for some value added application? And so when we looked at the different markets, there's some limitations in the ability to use algae as a food, particularly if you're using the algae to clean wastewater. You don't want to eat it afterwards, right? Like it's too close, too soon.
Probably not.
There's regulations against that, and so you can't really do that. Nor can you really easily feed it to animals either. I mean, maybe you can under some specific circumstances, but in general, it's not really advised. So we didn't really pursue that. Soil amendment and fertilizers are the main ones. So that's probably the most routine application right now. Is we're going to grow the algae, we're going to take the leftovers, we're going to use it as a fertilizer, and that fertilizer, it's more of a slow release fertilizer, so it's better for the land. It doesn't, when it rains, doesn't just wash right off back into the local watershed. But what it does is it slowly releases that nutrient back so plants can absorb it. And algae, most people probably don't realize this. I didn't know this. Algae lives in the soil. There's algae in dirt. In fact, the very first species of algae we ever isolated, I went with my postdoc back in grad school, like day one, and I thought we were going to hop in a car and go drive to some like lake or something, a pond or at least a creek. And we didn't. We jumped a fence and walked around the back of the building and pulled some dirt out of the ground, out of the forest. And he's like, all right, let's go see what we got. And sure enough, in a week, we basically put that soil in some water, added some nitrogen and phosphorus and some other micronutrients, put it under some light, like a little fluorescent light, and we waited for like a week. And a week later, turned bright green. And then we took those strains out, we separated them, we isolated them, we identified what they were. It was chlorella, super common species was just living in the soil behind the lab. So that's what we started. We actually used, ironically, we used that strain for years. It was it was super robust. It grew really fast. It was native. It was natural. Didn't produce a lot of oil, but that was what we did with Algix. Is we looked at taking the algae, using this high protein content that's in these fast growing strains. When the algae is growing exponentially, it's doubling its biomass every day or two, which was remarkable compared to a tree. It grows at 10 to 100 times faster than plants and trees. So that growth rate is really, really high. And so when you look at what you can do with it and what it's made out of, once you get enough of it, it's proteins and minerals. And typically proteins and minerals don't have a lot of use cases outside of, within fuels. You got to look at things outside of fuels to use it for. And so there is a history of using proteins in polymers, and what are called polymer compounds. So a polymer is a chain of molecules all essentially bonded together in a covalent or really strong bond. But it's like a noodle. Imagine a bowl of spaghetti. This is like the classic analogy. A bowl of spaghetti is like a polymer. And when it's nice and hot and lubricated, these things can flex. They can move. They have some flexibility to them. And you can add sauce to them to make it more viscous or less viscous, or more stiff or less stiff, or higher density or lower density. So as you bend and stretch those polymers, those little noodles are slipping against each other. And as they slip, you get friction. And that friction is the forces that we experience when you bend a piece of plastic, or if you stretch a piece of stretch wrap. What's happening when you stretch that stretch wrap? All those little molecules that are all intertangled are stretching against each other. And so that's what the algae was doing. We found the algae had these proteins. These proteins, by definition, are polymer chains of amino acids. And by using heat, we could open up these polymers, extend them, detangle them, and make them more polymeric-like. And then we would essentially match those up with a base polymer of some traditional application. So if we were using, let's say, an application where we wanted a biodegradable, bio-based packaging product, we could take a base resin like PLA that's used for that, blend it with the algae, make a new pellet called a compound, and then we'd send that. What's that?
What's a base resin?
The base resin is essentially what we're blending the algae with. The algae is a powder. The powder has to be mixed with something, a plasticization agent, some way to plasticize the algae. So the way we plasticize it is we actually use a polymer. So the base resin is essentially another polymer.
And where does that come from?
So really, we in the early days, we were trying to use bio-based compostable resins. We did a lot of work in that area. Commercially speaking, it was rather difficult to find applications. We did find some, but they never quite worked out for us commercially. So what we ended up doing was really focusing on the types of polymers that a potential customer is already using. So we'd find a brand or a customer or a factory that's already buying plastic in truckloads and say, okay, what kind of plastic are you using? Let's replace as much of that as possible with algae. And we can start small, and over time we can incrementally increase that amount of algae and increase the displacement level. And the goal is to be able to do so without compromising the performance, the cost, the aesthetics. And so sometimes that number can be high, sometimes it's low. It just really depends on the project, and it depends on what that project is. Depends on what that base polymer or that base resin is. So today, after 12 years of trying to scale this thing up. The good news is the equipment to make it at scale is the same regardless of what polymer we use. So we have equipment that can run at over 1,000 pounds of production per hour. So a lot, 10 million pounds of this product we can make off our existing setup in Mississippi. And we can use that same equipment to make PLA, which is a biodegradable, or we can make EVA and blend it with EVA, which is more of an elastomer. It's a flexible rubbery material that's used in shoes, which will come relevant here in a second. Or you can blend it with other things. We have recycled polymers. We've done more engineered materials. We've done different types of agricultural products that would be biodegradable as well. So just adding the algae to a product doesn't. If you add algae to a biodegradable product, it makes the product more biodegradable.
Right.
If you're adding the algae to a non-biodegradable product, the product's still not biodegradable because it's not 100% algae. There's still a fraction of it that is a durable product. And we can
Gotcha.
go either way. Commercially speaking, we found more commercial success with companies that are using traditional polymers that want to become more sustainable. We haven't quite unlocked the, you know, scalable, perfect compound that can make these footwear specific foams and rubbers that's 100% biodegradable. There are some new materials coming out that's being developed. There's an opportunity. We're excited. I think this will come soon. But as of right now, the majority of the usage in the world is of durable resins. These are not biodegradable. And so by taking the algae, we're able to lock up nutrients, lock up CO2, sequester those, capture and sequester that in a durable good by putting it into the product.
But yeah, so that's the main difference between if that company is going to create a product, a plastic-based product, whether it's the rubber sole of a shoe or a plastic bag. If they're to use your product, it's actually carbon negative by using the algae versus what they're doing right now is they're pulling either coal or oil or gas, whatever they're getting, that the hydrocarbon, and then they're putting that into the plastic, and that has already created emissions, whereas the algae that you are collecting or growing, I'm not sure if you do any growth stuff, has drawn down carbon. So it might not be necessarily reducing the plastic waste issue, but it is decreasing CO2 emissions. I'm understanding that correctly.
You nailed it. That's spot on. That's exactly correct. And you touched on something else there about harvesting versus growing, because
Yeah.
so when we first started, there was nowhere to just like go buy a truckload of algae, right? And so we were literally buying food grade spirulina at $20 a pound, like day one when we first started, saying, okay, this is similar to what we'd find in one of these algae blooms, but no one's selling algae blooms. So so it wasn't easy for us to go get that. So we kind of simulated it with spirulina. Obviously, at $20 a pound, we're replacing something that's like $2 a pound. So we were like 10 times too expensive. We knew that was a problem. So we also looked at growing our own algae. The problem with that is it's very expensive to build and operate your own algae cultivation system. It could be anywhere from $50 to over $150 million to build that out, or even more, depending on scale. It's a big time investment. There are several larger farms that have been built in the name of biofuels that are being used now, mostly for nutraceuticals, not for biofuels at this point. But the concept's there, the technology's there. But what we found is that even in those situations, you still got to feed it. You got to feed it CO2. You got to feed it nitrogen, phosphorus. So if you're just going to build a farm in isolation, it kind of defeats the purpose somewhat, because while you might be able to directly air capture the CO2, you're having to bring in nitrogen and phosphorus from an external source that would allow you to essentially fertilize that, and that fertilizer typically comes from fossil fuels. So that really was off the table. So between a massive amount of capital and the ability to work with an existing waste stream, we really targeted utility companies as our target producer, which I had a pro and a con. I mean, the pro was ideally and ultimately that's what we need to do. Like, that makes the most sense. We need to be more efficient at how we clean our water. And every town, every community in the world, for the most part, has wastewater treatment. So these standard municipal facilities all of a sudden could become akin to having every community have their own oil well, right? I mean, who wouldn't want to have their own natural resource that they could recover and utilize and sell and make money on?
Turn poop into gold.
It's like, exactly. It's like green gold. So that's the concept. That's the framework that we're trying to build. But right now, utilities are incredibly conservative.
Mm-hmm.
I mean, they're slow. They're not risk takers. They do, so it's been a challenge convincing utilities that this is a real opportunity. Thank goodness we've been able to find forward-thinking brands that want algae to succeed and have been using through our product and through others, like maybe Scott Fulbright from Living Ink. He's doing a lot of really good work in this space as well. So we're getting the big brands out there talking about algae. And then that helps us, because when we go to a utility company and they're like, who are you guys again? What do you do? Algae, why? And you're like, well, here, just don't take our word for it. Check out these 150 different products from big brands all over the world that are using algae right now commercially in their product, and
Sure.
that typically gets them interested. So that's really how we look at it, is less about us growing the algae, more us working with utility companies or government agencies that are dealing with the consequences of not intercepting that pollution prior to it being released. So if you don't get if you don't get the nutrients out, they end up in the watershed, right? They end up in lakes, they end up in creeks and estuaries, and then you have these algae blooms that occur. And a perfect example of this is back in the 70s when the Clean Water Act went into place. They banned the use of phosphorus-containing compounds in dishwashing materials and clothes washing detergents. This is because the high levels of phosphorus are difficult to get out of the wastewater, and they ultimately lead to these algae blooms that can be very detrimental in nature. And so by using so for us, we've been working with the U.S. Army Corps of Engineers, a big agency called AECOM, and also other government agencies in China that have massive, large-scale natural algae bloom problems or wild algae bloom problems. These are lakes that are what's called eutrophic or hypereutrophic, which means that they have an abundance of phosphorus. And when that abundance is there, it results in these big algae blooms that are very bad. They can kill fish. They can make drinking water toxic. They can wash on shore and rot and cause methane and hydrogen sulfide and poisonous gas. So, I mean, it's bad news. So, ironically, the thing that could be so good currently is really bad. And the more and more that humans pollute, which seems to be growing like every year, these algae blooms continue to grow in intensity, in duration, and in frequency in different places. And they're moving farther north. We're now detecting algae blooms farther north than we've ever seen. I saw images recently of an algae bloom happening in Antarctica where nutrients were locked up in ice. The ice is melting, and all of a sudden the water around the ice is green. So, because algae can grow when it's in really cold water.
That's because of warming. It can grow in cold water.
It can grow in cold water. It can grow in hot water. It can grow in salt water. It can grow in highly basic water. Different species, but all these different organisms have genetics that allow them to thrive in these inhospitable conditions. Really, so which is an interesting point because that's what the scientists are interested in. We're like, all right, if we can find a species that can thrive in an inhospitable condition, that means that that's the only thing that's going to grow. We actually can control what we're going to get by growing it in a high basic solution or a super saline solution. So that's why spirulina and Dunaliella, these two specific strains of microalgae, are commercially viable, is because they're relatively easy to control because nothing else likes to live in a water concentration that has a salt concentration twice that of the ocean, or a pH that's like pH 10 or 11. It's like swimming in lye. You don't really, it's not good.
So where are you getting your algae from right now?
So we work with these utility companies as a main supplier for us. They're using the algae and harvesting it as part of the wastewater treatment process that intercepts the nutrients, the trace amounts of phosphorus and nitrogen and carbon before it enters the environment. So it's typically what's called a third stage or a tertiary treatment. So there's not that many places that do that, but there's a few. California, Salt Lake City. We got some going up in Wisconsin right now with our partner Clearis. So that's kind of the traditional route. And then also we work with government agencies such as the Chinese government and some of their contractors, as well as the U.S. Army Corps of Engineers and AECOM, to go out and harvest algae from big wild blooms that are problematic. And some of those operations, like the one on Lake Tai, is so big that they've got in abundance a huge amount of algae being harvested, and they've been drying it and containerizing it and shipping it to us, and we've been converting and processing it.
Those are some pretty diverse business partners to have, huh?
Yeah, it's been interesting. It's been interesting. Not always in a good way, but it's been fun, I guess.
I mean, but again, if there should be no waste in the world, everything should be used efficiently. And then what you're doing is a great example of that. Can you tell me a bit about the product itself, this master batch? Is there other different products, or is the master batch, the bloom resin, like the main thing that you're creating right now?
Yeah. It's a great question. This is the question always comes up. So we're a compounder. Ultimately, we produce what's called a master batch. That's industry jargon for a pellet. So our pellet is a concentrate That's what master batch really means. It's a concentrate, and it contains about half algae biomass by weight. The other half is a polymer. That polymer, we have different flavors depending on the end use application. So if you're trying to make a foam and you want to make it for a sock liner or an insole of a shoe, you're going to use what's called EVA. If you're trying to make something more rubbery, like an outsole or a grip for bikes, that's going to be something called TPR, which is a different formulation. But same algae, different base resin, or different polymer side. The base resin is selected based upon these potential applications. We're also working with rubber as well. So again, kind of more for outsole applications. So we've really looked at a shoe, because that's where our customers are. Our customers are brands, many publicly traded companies and some private companies, but these fashion and footwear brands have strong sustainability initiatives now, and they're all looking for ways to improve their environmental footprint. And so when we look at those companies as being kind of the early adopters bringing in these new materials to market, we say, well, what product do they make and what's it made out of and how's it made? And that's where it all comes together, because we're able to go in and look at a shoe, look at all those materials that make up all the different components and say, okay, this part of the shoe is made from this polymer, this part's made from that polymer, and so we've sourced these polymers and used them, including both the virgin versions of them as well as the recycled versions of them as well. So we can get additional sustainable content in that finished product.
So the benefit for them is that the plastic, not the polymer, is it called the polymer or no? Or is that something
we
else?
call it a compound because ultimately it's a blend of the two. And so when we put algae into a product, we know that from our LCA, which is a third-party life cycle assessment that looks at all of the inputs into a process and all of the emissions of a process. Our process is carbon negative. It's absorbing CO2 through the process of algae harvesting and our algae growth, and then we're harvesting that. It's being processed and converted and being used to displace a petroleum-intensive product like plastic. So there's a big difference there between how much CO2 a plastic releases versus how much algae releases. Right, algae is actually sucking in carbon, and so we can quantify it on how much water per gram in the product.
So what if they took oil and didn't burn it for fuel and just made plastic out of it? Would the algae still be drawing down more than something like oil would?
Yes, there's LCAs on that. It does. Yeah, it's still pulling down CO2 out of the atmosphere. So it's pulling in a renewable CO2, right?
Right.
It's
of course.
ambient CO2. Yeah. It's not being mined. However, it's we could, in our process, we could do both. If you had a source of algae that actually had a high enough oil concentration that it made sense to extract it, let's just say it's 20%, which honestly is probably about right for production scale. I mean, you can get higher than that in a lab, but in real life, 20%, maybe 25% is kind of your like upper window for practicality purposes of how much oil is in the algae. So if you're to pull that oil out, you could take that oil, you could use it for food, you could use it for nutraceuticals or supplements. You could feed it to animals as a high-value fish feed. All those are, I'd say, higher value applications, pretty high value. Some are very high value applications, like the EPA oils and stuff. Or you could burn it, and you could transestrify it to make a fuel out of it. Or you could even use it in you can convert that oil into a polyurethane, to a polyol, and then combine it with a cross-linking additive that makes a polyurethane. So you could basically make a thermoset polymer versus what we do is thermoplastics. The difference being a thermoset is a chemical plastic. It creates a plastic structure through chemical reaction, whereas thermoplastics, what we do, the polymer is already present, but heat allows that polymer to deform and shape. So you can do injection molding, you can do extrusion, you can do blow molding. You can't do that with thermosets, right? Like that's a different kind of process. The difference between like when you go to the store and you buy epoxy that has two parts that you mix together, and you better use it quick or it's going to turn into rock. Like that's what thermoset chemistry is, versus let's say a plastic like a heat shrink or something, or some sort of thing that you can melt and it can form and reshape and cool and then be solid again. So those are the two applications that we look at. And when we look at the rest of the biomass, if you pull the oil out, you still have this 80% fraction or more that's not being used. And if you're growing the algae in such a way that it's not really useful for food or feed, then we can take that residue and put it into this thermoplastic process that we do at Algix to make this master batch, these pellets. And those pellets now, ironically, even though we didn't produce oil, we're replacing a material that was oil derived.
Right.
So we're replacing an oil. We have a lot of more value compared to like burning it as a diesel fuel or an ethanol fuel. It's way more valuable per pound. Maybe 5 to 10 times is more valuable. And so, and we're getting the yield. Compared to getting 20% yield, we're getting 100%. So we're getting 5 times more material out of the algae. Right, we're getting the whole algae, and then we're taking that, blending it, and then getting more value out of that finished product. And then we're using it in a market where we're not trying to make super cheap little widgets or packaging stuff that just gets thrown away where there's no value. We're really focused on high value products. You're working with these footwear brands where you're creating a pair of shoes that might be worth $100, $200, $500 in some cases. Mm-hmm. So now, for us to get going, those companies are going to have a little bit less resistance to pricing. They're still resistant. They still don't want prices to go up, but it is better.
Right. I did want to talk about price, but before that, I'm wondering if you took one of your pellets and then, for example, an airsoft BB and put them next to each other and then had 10,000 years go by, what would happen to your algae-based plastic pellet and then the airsoft pellet in comparison?
Well, I've never been asked that one. That's a good question. Well, we don't know exactly for sure, but it totally depends on what our pellet is made out of, right? The little normal little airsoft BBs are probably like a polypropylene or polyethylene or something. So they're going to last for probably at least 1,000 years, if not longer, right? They're super resistant to having moisture or microbes break into them. And if they do break in, which they eventually will, even so, they're like eating from a microbes perspective. That's like eating cardboard. There's not a lot of nutritional value in that polymer, in that polyethylene, as an example.
Right.
Now, in our pellets, let's just go with our main version. There's 2 examples on ours. When we first started, we were doing PLA. So PLA was the biodegradable. In that situation, our pellet would be gone in 6 to 8 weeks, most likely. Worst case, maybe 6 months, depending on the conditions. Okay. It would go away very quickly. The algae acts as a superfood and is infused throughout that polymer matrix, and it's also slightly hydroscopic, so it increases the probability that moisture is going to break into the part. And when moisture does break in, that means that bacteria can start to grow. And once bacteria starts to grow, and it's surrounded by the superfood of the algae, it's going to very quickly consume it, and it's going to break down. And we have done experiments with that. But that's not our main business at this point. We can make those, we do make that, but it's not something we make all the time. On the other hand, if you look at our pellets that are being used in the footwear industry, these are blends of algae with EVA. EVA is very similar to polyethylene. It's almost 80% the same thing. So that polyethylene fraction is not particularly digestible. It's not particularly nutritious for the microbes. But you're infusing it with algae. So over time, we suspect that there will be additional degradation. It's not going to last 1,000 years. It's going to last less than that. But it's also the same token not going to be compostable. We're not going to be able to certify it as a compostable material like you could with the PLA or some of these other resins that we've played with. So I think fundamentally the algae pellet would last a lot less time, but how long depends on the circumstances of what it's made out of and what the conditions are.
Well, in my thinking, maybe if you want a product to last a long time, you might be opposed to that. I'm thinking there's so much plastic garbage everywhere that if we had more algae, that would be better if stuff was made out of that. At least it's more likely to break down instead of just poisoning the environment with microbe nutritious food everywhere. You know what I mean? So I talked to this guy who's an expert. I mean, he's as into mushrooms or fungi as you are into algae. And he told me about the Carboniferous period, which I had never known about. And it's this one period in one of the epochs where these something learn the fungi couldn't break down the carbon molecules, and that's where all the fossil fuels come from. So it's putting out into the environment the only thing that exists that we can't like get rid of and bring into something like better. It's just stuck as what it is. It's just going to stay there and just weigh down the planet. So as far as like someone who, let's use the sneaker example, someone who's making shoes, how does your master batch compare to using plastic on price? And if we were to put a price on carbon, because it's we know that there's an unpriced externality that's making fossil fuel based products cheaper than they should be. How does yours currently compare? I'm curious.
Yeah, it's a great question. So we sell the pellets at, it's about $5 a pound. It's expensive compared to some of the stuff we're displacing. So we do get a premium right now. However, as I mentioned earlier, this is a concentrate. It's not being used 100%. When we work with footwear brands, there's several constraints that we deal with: color, performance, cost, and the aesthetics of it, like color is part of it, also like speckling or surface finish. So these different parameters really dictate how much of the pellets we ultimately will use, and it's not really our decision. It's more like a factory decision. That's the brand. I mean, the brand will ultimately say yes or no and define the spec, but the factory. Most people don't realize this. Like the footwear brands that we all wear and buy and love, and Nike, Adidas, all these different brands. They really don't make anything anymore. They design stuff, they prototype stuff, they market, they do a lot of stuff. But actually making the shoes is not typically one of the things that anybody does. All the supply chain, all the manufacturing is done by a very complex network of independent factory partners, mostly in China. Although there's been a big run over into Vietnam over the past few years. COVID kind of pushed some stuff back into China, actually, because of the closures this past year. But what we're finding is those factories are really the ones that are kind of dictating how much algae we can get in there routinely. And when we do that, typically we find that our average project is around 20%. And that means that an average footwear brand may spend an extra 15 to 20 cents per pair using Bloom in their shoe at some level compared to a virgin material. So it's, for a shoe that costs $150 or $100 or even $80, we're talking, 10 to 20 cents typically is our cost factor. Now, the value they get out of that is that once they launch that shoe, we use the global recycled standard to track all of our materials. We use the LCA process to quantify our benefit, and then we can issue a certificate to the brands that says for this specific shoe, it's cleaned, 50 liters of water based on the algae growth, and it's reduced the CO2 emission by, X number. And so we're quantifying the measurements, and that brand is then putting that on a hang tag, or they're putting it on the box, or they're putting it. And then at the end of the year, we say, okay, you guys did 100,000 pairs, or actually, I mean, as an industry, we did 17 million pairs in 2021. So like it becomes a big number. We issue a stock certificate of that carbon credit and of that water cleaning credit to the brands on in written form, in paper form, and we send, and we also have it in digital form as well. We'll probably go full digital just because we don't want to be sending paper all over the place. But these certificates ultimately can be used in the brand's final ESG report. So at the end of the season, a brand is going to report to their shareholders, hey, here's what we did to improve our environmental impacts. Bloom now has its own little page in these reports to say, hey, we use Bloom. Here's our certificate. Here's our impact. This is great. We're moving, and we're going to do more next year. And so that's where the brands are getting the value for using the material.
And you can put it on the box with Scott Fulbright's Algae.
100%. Scott and I have been talking about that actually specifically.
I'm starting to realize I think your thing is going to explode at some point. I think it's going to completely flip eventually to just using everything's going to be made from algae. It seems like the most. Wow. I mean, it's just cool to be here like before that's happened talking to you. And I can see just based on market indicators, it's just very obvious. When you talk about only 10 to 15 cents right now, and that's with huge tax incentives, or what are they called? Tax subsidies, government subsidies on oil and gas, that's making it artificially cheaper than it is, not taking into account the absolute devastation that's going on our planet. Would you mind just telling our audience how many liters of water your company's cleaned up so far? Because I thought that was pretty cool.
Well, we just did a big press release. So we just hit 1 billion liters of water cleaned. And that's calculated again by how much water we're having to clean and filter to get to remove the algae from production. So it's a very practical number, and the cool part about that number is that we've actually taken one of the biggest challenges that I was facing as a grad student, trying to get algae commercial. The number one issue was how are you, like, particularly, like, let's say 15 years ago, the big issue was how are you going to make biofuels if you're spending energy harvesting algae? You gotta harvest it really efficiently, because if you spend a bunch of energy to do it and then you take that algae and burn it, your LCA doesn't work. The benefit analysis doesn't work. You actually end up releasing more carbon than you save by doing it. So that's been a critical thing. Now with the plastics market, it's a lot better because you're not just looking at burning something. It's got this much more complex life cycle assessment study. So we look much better there. However, the interesting thing is that when you look at the amount of carbon that's being absorbed by the algae, it can, and you look at this at a global perspective, algae as a whole, and I mean like phytoplankton, seaweed, the whole ecosystem of quote unquote algae around the planet is said, according to the research, to absorb as much, if not more, CO2 than all of the forests on the planet combined.
Is that because of the ocean?
It's because the planet's 70% water.
Yeah, for the phytoplankton in the ocean, right?
It's the phytoplankton, and to some extent the freshwater blooms as well. And in the sea, the coastal regions are incredibly productive. So a combination of coastal regions that are getting upswelling of nutrients have lots of diversity. But so the algae not only represents a diversity or an ability to improve the diversity of organisms outside of algae. Fish and little crustaceans live in the algae and feed off the algae. It's the basis of the entire food chain of the planet. So, when we look at our current petroleum reserves, the petroleum's actually ancient algae blooms. These are long ago blooms that were buried, and converted into fossil fuel reserves through heat and pressure over time. What we're looking at now is these blooms are still happening in a different way, but they're still happening, and they're happening closer to society, quite frankly, because they're happening near all of our pollution. And so we have the opportunity here to use the algae in a way that decouples us from the algae blooms of the past. I mean, eventually those blooms are going to be harder to find, harder to get, more expensive, and we're just not going to be able to release that much new carbon into the atmosphere without detrimental consequences. Certainly. So if we can use algae that's already growing in nature and find a way to do so efficiently, it's going to really improve our ability to sustain the planet.
Yeah, another thing I wanted to bring up during this conversation is that the more we burn fossil fuels, the more likely it is that the algae blooms will continue to grow and become bigger. Because, and correct me if I'm wrong, it's because there's a greening effect that happens when you increase CO2 concentrations in the atmosphere, because plants feed off of carbon. So they're using sunlight and they're converting the carbon into glucose, whatever, and making their bodies. So there's actually a huge opportunity to take the carbon that's in the atmosphere and turn it into your product, or it's going to turn into algae, or we can sequester the algae in the ground, or we could turn it into products. I'm accurate on that, right?
Yeah. Oh, 100%. The elevated levels of CO2 are accelerating the rate. The warming temperatures are making water warmer, which means faster algae growth. And then you combine that with eutrophication, the nitrogen and phosphorus. We've got this perfect storm. And here's the issue, though. We actually have termed this the climate change engine. So as these algae blooms happen, they get worse, they get bigger, and we're not harvesting them. We're harvesting a little bit of them, but through our partners and stuff. But for the most part, none of the stuff is getting collected. Right? It's all just rotting. It's dying and rotting and decomposing. And when that happens, it releases methane back into the environment. Methane's a much more potent greenhouse gas than CO2. So there's a recent publication out of Nature Communications, talking about this greenhouse gas emissions from the eutrophication impact. And that's a newer concept that is not like mainstream. It's not modeled in IPCC, which is the Intergovernmental Panel on Climate Change. So point being, the situation's is worse than we think it is because of these algae blooms, and it hasn't quite caught up with like the global politics in terms of, what is the long term trajectory for greenhouse gas emissions. And with these blooms, the algae blooms growing and then busting and then decomposing, and then happening faster and faster and bigger in more areas, it's releasing more and more methane, which is 24 to 35 times more potent than CO2. So the impact is like way more. And so we just did a new LCA where we pulled in this latest research and latest data. We handed all this over to our independent auditors and analyzers for this LCA. They reviewed all the data. They then sent it to a panel of experts that reviewed the data, and they put together a new model that shows what's the big impact. What's the net impact of using bloom? And it's more than just the CO2 the algae captured. It's also preventing that CO2 and that biomass from being converted into methane. And it's a huge difference. It's a big difference. So with that, we're able to provide even more positive impact when a brand uses even a little bit of bloom, because the whole shoe's not made out of algae, right? We're putting, in some cases, very small amounts of algae in these shoes. In some cases, we're putting more. It just really depends on the project. Every project's different. But regardless of what the project is, even if it's a small amount and it's a big brand, they may be more cost conscious. They might be putting it into millions of pairs of shoes. So while per pair may be small, the actual overall impact could be enormous because they do so much volume. And so we don't tend to think about our projects in terms of like, what's the highest we can get in this one specific part, although we want that number to be as high as possible. At the same token, we recognize that like we really can't control it that much. The bigger question is, how do we get this brand to adopt bloom in everything they do? Right. And we find that let's just get in the door at the minimal threshold. Let's get them to understand and wrap their minds around this. Let's get their marketing team starting to think in this regard. And then it's going to be a lot easier to say, well, let's add it to this other product line, or let's increase it by 5%, or let's do it in this part and this part and this part. Let's use more parts of the shoe.
What is your vision for the future with all this stuff? I can see far ahead. I'm wondering, where do you see this going?
Well, if talking about how algae is the fundamental regenerative source of the planet, right? It's cycling our CO2. It's our major carbon sink. It's the reason people talk about the oceans being the largest carbon sink. It's because of photosynthesis in the oceans that's utilizing that CO2. Otherwise, the pH would just drop in the ocean, and it is dropping a little bit, but it's not dropping as much as it would. So, algae is this natural, abundant, untapped resource that humans really have yet to conquer, and certainly electrification is. I mean, one of the main reasons I stopped pursuing the biofuels was that this was like in 2007, 2008. I was really interested in this little electric sports car that this kind of mad scientist guy was working on. And I remember sitting in grad school, like in 2008, probably this point. And I was like, man, if this guy's successful, this is going to change the course of automotive history. And, obviously I'm talking about, the Tesla Roadster and Elon Musk. And so I never would have expected it to turn out quite like it has. But to me, that's like, all right, I think we can find ways for mobility to solve with electrification. Now, there's still issues with airplanes and jet fuel. That's still a problem. It's hard to electrify jets. Maybe possible, but not simple. Also, there are maybe some other applications that you need a combustible fuel for. So I don't think, fuels are dead per se, but there's probably better things that we can do with the algae till we get to that scale. Mm-hmm. So when we looked at how do you scale this thing, how do you ramp that kind of production, you don't start with the cheapest thing possible and try to dominate that. You're going to die. You've got to start with something valuable but also scalable. So we thought polymers was kind of this nice middle ground. It was directly impacting and reducing greenhouse gas emissions, reducing petroleum, replacing it in a way that was compelling to the Department of Energy and government grants and agencies and the public in general. But then we're able to take that and say, okay, how do we, focus on the next market? So footwear is kind of our thing right now. 90% of our projects are footwear focused. 10% of us is automotive. 10% for Bloom. 10% is automotive materials. Within that 10%, we're looking at furniture. We're looking at other consumer products. Maybe even some packaging products. And so in the future, I could see algae being used for, we talked about living ink, inks, fibers. Algae Knit is another company making really cool fibers that are biodegradable from kelp, from seaweed. We're looking at, the bloom materials. You're also looking at foods, being able to produce foods and also produce enzymes that, when fed to cattle, can reduce their methane emission to make cattle's farming more sustainable and generate less greenhouse gas emissions. So there's just so many areas, and since there's so many species of algae and they're so diverse and they grow in so many different areas, it's like right now there's a lot of companies are just looking at the genetics and say, okay, if we can take the genetics of this species and grow it in large scale, what's the benefit? What can we overcome, or bring in other like transgenic stuff? You could bring in, like I was talking to a really cool professor recently about, they've isolated a squid protein that makes amazing biodegradable elastomers, like a thermoplastic elastomer that's very flexible and rubbery. But it's from the teeth of squid. Who would have thought, right? And now they can produce that in large quantities by using bacteria. They usually grow bacteria. The bacteria has the squid genetics in it, and they can produce this compound. So that's like another cool thing. That's there's all this stuff. There's also other people like Checker Spot that are out there doing amazing work where they're growing genetically modified strains of algae that can produce these high value oils. And those oils can be used in material applications, polyurethanes and other applications that provide. It's not just sustainability, but actually performance. And that's where I think when you ask about where the long term is that we'll be able to leverage some of this unique genetics and unique organisms in manufacturing processes that will allow us to switch everything over to be sustainable and love it and like it. It's not like we're making all these compromises. Yeah, the clothing performs better. The materials are stronger. The flexibility, the durability is even better than before. So, products are more compostable. All these different factors depends on what you're trying to make. I think all these things are going to play into the future when these technologies start to mature and commercialize to the scale that we need to see very soon.
Ryan, I just want you to know, you're bringing up Elon Musk in 2008, and you say you were looking at him saying that he was going to change the world. I'm 24 right now. I'm at like the master's, point in my career. Like I'm starting my business. So I graduated from college. I'm looking at you right now, man. You're in that seat. So keep doing what you're doing. It's awesome. There's a massive opportunity, and he's helping the world a lot with what he's doing. Some people have criticisms of him. I love Elon Musk personally. I think a lot of people do as well. I think you just see criticism on the news. But it's been great having you on the show, man. Any final... Oh, I don't want to give a huge shout out to your YouTube page because that thing is awesome. And why don't you tell me a bit about the podcast that you're starting before we sign off here as well?
Yeah. So, you can follow us, bloommaterials.com. We've got, Instagram, LinkedIn. I'm very active on LinkedIn. You can follow me personally, Ryan W. Hunt. Also, Bloom Materials is on there as well. And then we just started our Bloom Bloom Sustainable Material podcast. So this is a new venture that we started this year, doing a similar thing as you, Ethan. We've realized that there's just needs to be more discussions with the brands and some more transparency to help our customers and the audience really dive deeper into some of these topics, because they're you can't just take the 30-second little blip that you see in the news. It's not quite that easy, and there's so much more fun stuff to talk about. So we're bringing on our partners, our algae producers, our footwear brands, people from the industry, scientists, to talk about a wide range of topics related to algae, sustainability, sustainable materials, innovation, and really manufacturing of the future. Because that's where it's going. Is that our current supply chain is broken. This whole COVID situation and all the geopolitics that are unfolding right now. It's been a disaster. It's been really challenging for us as a small startup company to try to navigate this global supply chain and all these problems. It's been a major challenge. So as we are scaling up and as we are finding new markets and finding new customers and building trust with them, we want to be able to encourage them to explore more innovative, more sustainable and really more revolutionary ways of making products that can be decentralized. We don't have to be reliant on just one area of production. I mean, sure, China's not going anywhere, right? We're still going to get a bunch of stuff from China, but the more that we can create some backup plans in different parts of the world for those local communities, those are going to help us unlock this holy grail of circularity. Circularity is this idea of cycling materials over and over again. Well, if all of our manufacturing is done in one country, far on the other side of the world, how's that ever going to work? The LCAs don't work. The techno-economic analysis doesn't work. We need to have these materials looping in a more decentralized way. And that's where I think the future's heading.
And all I'm saying is, if you're American, you might consider investing in Vietnam, giving them some business. We might owe them a little bit for some stuff we did in the past. I'm just throwing that out there. Ryan, it's been great having you on the podcast. Any final pieces of advice for young folks who are passionate about building a better world or starting their own company?
Oh, man. Well, you've got to find something that you really love, and you've got to find a big problem, and in these problems, you got to have patience. You really got to love what you do, because it's not. I mean, we've been at it 12 years, and I feel like we're still in the trenches every day, right? And so it doesn't really get that much easier. I'm hoping eventually it does. I don't know if it will or not, but yeah, I'd say pick something that you think is really going to be revolutionary, has purpose, has meaning, has positive impact, and support each other. I mean, that's the biggest thing. Is if you're friends or network with other people, use LinkedIn. LinkedIn's probably been the most amazing resource that we've come across. Being able to connect with people at that kind of professional level and identify partners and customers and employees, teammates from that platform has been really huge. So, yeah, and always, I think impact. Focus on the impact. That's really, I think, what we've realized is that if you focus on impact, the rest will shake itself out. But focus on things that provide the most positive impact, and we think algae is one at the top of that category.
I think you've made the case for that quite obvious today, man. Cool. Appreciate the time, brother. All right, everybody. We'll see you on the next one. Peace out. So if you or anyone else you know is looking to buy or sell a home anywhere in the USA and would like to create thousands of dollars in donations without any cost out of pocket, please visit ccrealty.org today.